Swayam Prabha. Digital India. Educated India.
Welcome to lecture 13 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Estimation under Stochastic Restrictions. So, often in many applications we have some prior information about the regression parameters along with the sample information, and we can express this prior information in the form of linear restrictions. In lecture 8, we discussed the estimation of regression coefficients in the presence of a set of exact linear restrictions, and then we developed restricted regression estimator for the regression coefficients. Again in lecture 9, we also discussed and developed testing procedures for testing the set of linear hypotheses. Now, sometimes in many applications, although we have some prior information and we are able to express the prior information in the form of linear restrictions, but there is some kind of uncertainty involved. The restrictions are not exact, and as you know, if we consider restricted regression estimator, and if the restrictions are not correct, then it may lead to the biased estimator. So, if there is some sort of uncertainty in the set of linear restrictions and we do not incorporate it at the estimation stage, then your restricted regression estimator may be even worse than the ordinary least square estimator because of the bias. So, to accommodate such kind of uncertainty, we may consider stochastic linear restrictions, which is the subject matter of this lecture. So, along with the sample information contained in your linear model y equal to x beta plus u, we also have a set of stochastic linear restrictions, and then we combine this set of stochastic linear restrictions with your model, and then we develop a proper estimator for the regression parameters. So, such kind of estimator is called the mixed regression estimator. So, we will also discuss the properties of the mixed regression estimator in this lecture. So, in exact linear restrictions, there is no randomness involved in the auxiliary or prior information. Your restrictions are exact, and you say that there is no uncertainty involved in your restrictions. Now, in many practical situations, some uncertainty may be involved in restrictions. So, if there is some kind of uncertainty involved in the restrictions, then of course, for proper inference procedures, you must incorporate this uncertainty at the estimation stage. Say, suppose we consider this model y equal to beta 1 plus beta 2 x 2 plus beta 3 x 3 plus beta 4 x 4 plus u. Then in repetitive studies, suppose on the basis of past experiments, estimates of regression coefficient beta 2 and beta 3 are available along with their standard errors. So, you also have some past information based on the past experiments, and then you have estimates of regression coefficients beta 2 and beta 3 along with their standard errors. And in the past experiments, you observe that the values of beta 2 and beta 3 remain stable around 2 and 1 respectively. Of course, all the time it is not equal to 2, it may vary, but it varies around 2. Similarly, the value of beta 3 varies around 1, and their standard errors are 0.5 and 0.8. So, you have some kind of prior information, the values around which beta 2 and beta 3 vary and the standard errors. Then you want to express this prior information. So, you can express the information as, say you write 2, 1, these are the values of beta 2 and beta 3, or actually the values around which beta 2 and beta 3 revolve, and then we take a matrix 0, 1, 0, 0, 0, 0, 1, 0, because you have to pick beta 2 in the first row and beta 3 in the second row. So, we take the element corresponding to beta 2, means the second element of the first row equal to 1 and all other elements are equal to 0. Similarly, in the second row we take the third element equal to 1 and all other elements are equal to 0. So, that you can pick beta 3, plus you have a random error term V 1 V 2. Then expectation of V 1 V 2 equal to 0 and the variance covariance matrix of V 1 V 2 is say 0.25, 0, 0, 0.64. So, expectation of V 1 square is equal to 0.25, or you can say the standard error of beta 2 or V 1 is 0.5 and the standard error of V 2 or beta 3 is 0.8, and we write this matrix equal to psi. So, you can express this prior information, the prior information that the values of beta 2 and beta 3 revolve around 2 and 1 with respective standard errors 0.5 and 0.8 in this form. Now, suppose you write this vector 2, 1 as small r, and then this matrix, this is your small r, this is your capital R, and this is beta, and we write V 1 V 2 as V, vector V. Then you get the restriction R, small r equal to capital R beta plus V, where expectation of V is 0 and expectation of V transpose is equal to psi, and psi is given here. Now, we consider another example of Cobb-Douglas production function. So, we take log of the Cobb-Douglas production function log y equal to log a plus beta 1 log L plus beta 2 log k. And then suppose along with the assumption of diminishing returns to scale, you also have the prior information that beta 1 plus beta 2 is greater than 0. So, that beta 1 plus beta 2 lies between 0 and 1. So, instead of exact linear restriction, you have some kind of inequality restriction. Beta 1 plus beta 2 lies between 0 and 1. Now, suppose we treat these bounds as say 2 sigma limits, say mu plus minus 2 sigma. Then mu plus 2 sigma is equal to 1 and mu minus 2 sigma is equal to 0, and this implies that mu is equal to half. You just solve these two equations, you get mu equal to half and sigma equal to 1 upon 4. So, using this we can express our prior information, which is beta 1 plus beta 2 greater than 0 less than 1 as beta 1 plus beta 2 plus V 1 equal to 1 upon 2. Say beta 1 plus beta 2 plus V 1 equal to mu. Then expectation of V 1 equal to 0, expectation of V 1 square is equal to 1 upon 4 square, that is 1 upon 16. So, since it is difficult to accommodate this kind of inequality information in estimation, so we express this inequality as say in the form of 2 sigma limits, and then we take mu plus 2 sigma equal to the upper limit 1, mu minus 2 sigma equal to the lower limit, that is 0. So, that you get mu equal to half and sigma equal to 1 upon 4, and then you get this restriction. Now, we consider estimation under stochastic linear restrictions, and the resulting estimator is called the mixed regression estimator. So, we consider the model y equal to x beta plus u, expectation of u equal to 0 and expectation of u transpose is equal to sigma square u I n. Then the restrictions on the coefficients factor, that is beta, are stochastic and given by small r equal to capital R beta plus v. So, along with the restriction small r equal to capital R beta, this is the exact restriction if you do not include this part plus v. But here along with the restriction small r equal to capital R beta, we also have plus v, and this makes the restriction stochastic, because v is a random variable, and then expectation of v is taken as 0, expectation of v transpose is equal to psi, and we assume that this psi is known. So, how much uncertainty is involved in defining this restriction small r equal to capital R beta, that uncertainty is known. In the previous two examples also, we know the value of capital psi in both the examples. Again, we assume that expectation of u v transpose is equal to 0, means these prior restrictions are uncorrelated with the sample information. Some possible reasons for stochastic linear restrictions are, say, stability of linear functions of regression coefficients. So, suppose you consider this model y equal to beta 1 plus beta 2 x 2 plus beta 3 x 3 plus u, and suppose on the basis of past experiments you come to know that the regression coefficient beta 2 minus beta 3, or in fact it is the difference of these two regression coefficients beta 2 and beta 3, this remains stable around 1 for several years. and the standard error is 0.5. Then you can express this prior information in the form beta 2 minus beta 3 plus V equal to 1. And then you can write it as 0, 1, minus 1, and then you take beta 1, beta 2, beta 3 plus V equal to 1, or you can say r beta plus V equal to small r, and expectation of V is taken as 0, expectation of V square is equal to 0.5 square. So, it is 0.25. So, you get this restriction. So, you can express the restriction beta 2 minus beta 3 equal to 1 with some uncertainty in the form of these linear stochastic restrictions. Then the second example which we had taken was we had some prior information in the form of some inequality. So, sometimes you have prior knowledge in the form of inequality restrictions. Say economic theory often translates into the form of inequality restrictions on parameters, and then you may prefer to write those inequality restrictions in the form of linear stochastic restrictions. So, for example, economic theory implies that goods which are necessities with no substitutes have low price and income elasticities of demand. So, such kind of goods have low price as well as low income elasticities of demand. So, suppose demand is equal to beta 1 plus beta 2 price plus beta 3 income plus u. Then beta 2 is the price elasticity of demand, beta 3 is the income elasticity of demand, and then we may express the economic theory as mod of beta 2 lies between 0 and 1, or beta 2 lies between minus 1 and 1, and suppose beta 3 lies between 0 and 1. So, this is your prior information, and the prior information is in the form of inequalities. So, you have these inequalities as your prior information. Now, suppose we treat these bounds as p sigma limits. You may take p equal to 2 or p equal to 3. It depends upon your belief about the prior information. So, suppose we take p equal to 2. Then suppose mu 1 is the mean of beta 2 and mu 2 is the mean of beta 3. And then mu 1 minus 2 sigma 1 is equal to minus 1. This gives you the lower limit, and mu 1 plus 2 sigma 1 gives you the upper limit. And then we solve these two equations, and then we get mu 1 equal to 0 and sigma 1 equal to half. Further, mu 2 is the mean of beta 3. So, mu 2 minus 2 sigma 2, which is the standard error of beta 3, is equal to 0. This gives you the lower bound, and mu 2 plus 2 sigma 2 is equal to 1, the upper bound. Again we solve these two equations, and then we obtain mu 2 equal to half sigma 2 equal to 1 upon 4. So, now you can express your inequality restrictions in the form of stochastic linear restrictions. So, we express the inequality restrictions as say beta 2 plus V 1 equal to 0, that is beta 2 plus V 1 is equal to mu 1, mu 1 is 0, and then expectation of mu 1 square is 1 upon 4, because sigma 1 is 1 upon 2. Then beta 3 plus V 2 is equal to 1 upon 2, because mu 2 is equal to 1 upon 2, and expectation of V 2 square is equal to 1 upon 16, because sigma 2 is equal to 1 upon 4. So, you get the stochastic restrictions are beta plus V equal to small r, where capital R is equal to, say, in to get the first relation, we take the first element of first row of capital R equal to 0, then the second element which is corresponding to beta 2 we take as 1, and the third element we take as 0. Then to get this inequality, so we want to pick this beta 3 from the regression coefficients vector beta. So, we take the first element of the second row equal to 0, second element 0, and the third element 1, and then we multiply it by beta 1, beta 2, beta 3. So, in fact, we get beta 2, beta 3 here, plus V equal to small r, and small r is equal to 0, 1 upon 2. So, you get the first relation as beta 2 plus V 1 equal to 0. The first element of small r is 0, and then you get beta 3 plus V 2 equal to 1 upon 2. Then the exact restriction r beta equal to small r is suspected, and element of the uncertainty is introduced in the form of random element V. So, this may be the third reason for considering stochastic linear restrictions. You have the exact restrictions, but you are uncertain about these exact restrictions. So, you want to introduce the element of uncertainty here. So, we introduce the element of uncertainty in the form of V, where V is a random variable having mean 0 and variance covariance matrix psi. Now, along with the model, you also have a set of stochastic linear restrictions. So, we combine this model y equal to x beta plus u, in which this u satisfies the conditions expectation of u equal to 0, expectation of u transpose equal to sigma square u I n. Then we combine the model with these stochastic restrictions small r equal to capital R beta plus V. Again V is of order q cross 1. So, obviously, this small r is also of order q cross 1. You have q restrictions, then q cross k, k cross 1, beta is of order k cross 1, then V is of order q cross 1. And we also assume that expectation of u v transpose is equal to 0. That is, your prior restrictions are uncorrelated with your sample information. These two are uncorrelated. and then combining these two, we can write y r equal to x r beta plus u v. So, here you have n rows in y and q rows in small r. Similarly, in x also you have n rows, in capital R you have q rows, and in u v also you have n and q elements respectively. And then we write z equal to y r, capital Z equal to capital X capital R, and w equal to u v. So, you can jointly write 1 and 2 as z equal to z beta plus w. Obviously, expectation of w is equal to expectation of u v, expectation of u is 0, expectation of v is 0. So, finally, you get expectation of w equal to 0. In fact, this 0 is a vector with all elements 0 of order n plus q cross 1. Then you can easily obtain the variance covariance matrix of W, which is expectation of W W transpose, then W is equal to U V. W transpose is equal to U transpose V transpose. So, actually you obtain expectation of U transpose, U V transpose, V U transpose, V V transpose, and then this is equal to expectation of U transpose is equal to sigma square U I n. Expectation of U V transpose is 0, expectation of V U transpose is 0, and expectation of V V transpose is equal to psi. So, you get this matrix and we denote it by sigma. So, this covariance matrix is non-spherical, and then we can apply the generalized least square estimator for estimating beta. And the GLS estimator of beta for model 3 or 4 is B m equal to 1 upon sigma square u x transpose x plus r transpose psi inverse r whole inverse 1 upon sigma square u x transpose y plus r transpose psi inverse small r. Actually, this GLS estimator is also called the mixed regression estimator. So, we now prove this result. So, we have small z equal to y small r, capital Z equal to x capital R, and then we obtain sigma inverse. So, sigma inverse is equal to sigma u to the power minus 2, we take inverse of sigma u square. So, you get this term I n 0 0 psi inverse. This you can easily verify. Now, you require this term Z transpose sigma inverse Z. Now, Z transpose is equal to X transpose R transpose. Then you have sigma u minus 2 I n 0 0 psi inverse, and then x r. So, this is equal to you get x transpose sigma u minus 2 x transpose plus R transpose into 0 here, and then you have X transpose into 0 plus R transpose psi inverse, and then you have X R here. So, this is equal to sigma u minus 2 X transpose X plus R transpose psi inverse R. So, you get this expression. Similarly, Z transpose sigma inverse small z is equal to, we have already obtained Z transpose sigma inverse. So, this is equal to sigma u minus 2 X transpose, then R transpose psi inverse, and then you have small z, which is y small r. So, finally, you obtain sigma u minus 2 X transpose y plus R transpose psi inverse small r. So, you get this term. Then the GLS estimator which we obtained from model 4 is B m equal to Z transpose sigma inverse Z inverse Z transpose sigma inverse small z. Then we substitute the value of Z transpose sigma inverse Z from this expression, and we also substitute the value of capital Z transpose sigma inverse small z from here. So, finally, we get this expression for B m. So, we have obtained this estimator by combining your model y equal to x beta plus u with the linear stochastic restrictions. So, after combining these two, we have applied the generalized least square procedure for estimating beta, and this is the resulting estimator. This estimator is also called the mixed regression estimator. Actually, you have mixed the sample information with the stochastic linear restrictions or stochastic prior information. And of course, when sigma square is u is unknown, we replace sigma square u by its estimator, and you know that the unbiased estimator of sigma square u is s square equal to 1 upon n minus k y minus x b transpose y minus x b. So, you can replace s square sigma square u by s square, and then you get feasible or operational mixed regression estimator. Now, we prove this result. We prove that B m, the mixed regression estimator, is an unbiased estimator of beta, and then the variance covariance matrix of B m is, so expectation of B m minus beta transpose equal to 1 upon sigma square u x transpose x plus R transpose psi inverse R. Now, you can write B m minus beta as, say, in the form of capital Z and small z, B m is equal to Z transpose sigma inverse Z inverse Z transpose sigma inverse small z, and then we write small z equal to Z beta plus you have W here, W is equal to u v. So, we get beta plus Z transpose sigma inverse Z inverse Z transpose sigma inverse W. So, you get this expression. Then if you take expectation of B m minus beta, then you obtain expectation of B m minus beta equal to Z transpose sigma inverse Z inverse Z transpose sigma inverse expectation of W, and expectation of W is equal to 0. So, you obtain expectation of B m minus beta equal to 0, or you can say expectation of B m is equal to beta for all beta. Therefore, B m is an unbiased estimator of beta. Next, we obtain the variance covariance matrix of B m. So, notice that B m is the generalized least square estimator of beta for the combined model small z equal to z beta plus W. So, the variance covariance matrix of B m is Z transpose sigma inverse Z whole inverse, because expectation of W transpose is equal to sigma, and actually sigma is equal to sigma square u I n 0 0 psi. Then we have already obtained the value of Z transpose sigma inverse Z, which is equal to 1 upon sigma square u x transpose x plus R transpose psi inverse R. So, finally, we obtain this expression for the variance covariance matrix of mixed regression estimator B m. Then you can easily verify that this B m satisfies the stochastic restrictions small r equal to capital R beta plus V, in the sense that expectation of R B m plus V is equal to small r, expectation of small r, because expectation of R B m plus V is equal to expectation of this term is R beta, and expectation of V is 0. So, you get R beta here, and expectation of small r is R beta plus expectation of V, and expectation of V is also 0. So, you get R beta. So, on average you can say, or after taking expectation, this mixed regression estimator satisfies the stochastic restrictions. Now, we compare the mixed regression estimator and OLS estimator. We compare the variance covariance matrices of mixed regression estimator and OLS estimator. Now, for that purpose, we require a result of the matrix algebra, and I am going to prove this result here. And the result is like this. Say, if A and B are two, say, n cross n matrices. So, these are two square matrices, and both A and B are positive definite also. Then the difference of matrices B inverse minus A inverse is positive definite if and only if A minus B is positive definite. So, the advantage of this result is that if you want to compare B inverse and A inverse, and if you want to check whether B inverse minus A inverse is positive definite or not, then you simply check whether A minus B is positive definite or not. And for checking whether A minus B is positive definite or not, you do not have to take inverse of A or inverse of B. So, if A minus B is positive definite, then this implies that b minus half a b minus half minus I n is also positive definite. We simply multiply pre and post multiply this a minus b by b minus half So, this matrix is also positive definite and this gives you b minus half a b minus half minus I n. And since this matrix is positive definite, this shows that all the eigenvalues of this matrix are greater than 0. All you can say actually the eigenvalues of I n are 1. So, you can say that the eigenvalues of b to the power minus half a b to the power minus half are greater than 1. Actually, the eigenvalues of this matrix are the eigenvalue of this matrix minus 1. So, the eigenvalues of this matrix greater than 0 means the eigenvalues of this matrix b minus half a b minus half greater than 1. Now, you can write b minus half a b minus half equal to b minus half a to the power half a to the power half b to the power minus half. So, we can write this matrix in this form. We also know that the eigenvalues of say a b are same as the eigenvalues of b a. So, eigenvalues of b to the power minus half, a to the power half, a to the power half, b to the power minus half and a to the power half, b to the power minus half, b to the power minus half, a to the power half are the same. Actually, what we have done is we take this b to the power minus half towards this side and then we take a to the power half also here. But the eigenvalues will not change and then we get a to the power half b inverse a to the power half. So, this shows that the eigenvalues of a to the power half b inverse a to the power half are also greater than 1. Again, this shows that a to the power half b inverse a to the power half minus I n is positive definite. Again, we pre-multiply and post-multiply this matrix by a to the power minus half. So, what we get? B inverse minus A inverse. So, B inverse minus A inverse is positive definite. So, this proves the result. Now, we compare the variance covariance matrices of the OLS estimator and mixed regression estimator. The variance covariance matrix of the OLS estimator is equal to sigma square u x transpose x inverse and the variance covariance matrix of mixed regression estimator is 1 upon sigma square u x transpose x plus r transpose psi inverse r whole inverse. So, basically what we want to do? We want to compare these two matrices. So, we take V b minus V b m and in case this matrix is positive definite, then we can say that BM, this mixed regression estimator provides an improvement over B, the OLS estimator. So, basically you have to show that variance of B minus variance of BM is positively definite. So, in fact, both of these matrices involve the inverse, if particularly this second matrix, which involves the inverse of 1 upon sigma square u x transpose x inverse plus r transpose psi inverse r. So, directly it may be difficult for you to compare these two matrices. So, we make use of this result, say B inverse minus A inverse is positive definite if and only if A minus B is positive definite. So, instead of showing that V B minus V B M is positive definite, we take V B M inverse minus V B inverse. Then V B M inverse is equal to 1 upon sigma square u x transpose x plus r transpose psi inverse r minus V B inverse is equal to sigma square u 1 upon sigma square u and x transpose x, and then this term will cancel out. So, you get r transpose psi inverse r here. Now, this is a positive definite matrix. Of course, our psi inverse is a positive definite matrix, because this is a variance covariance matrix. Psi is a variance covariance matrix. So, R transpose psi inverse R is also a positive definite matrix. And then this shows that V B minus V B M is also positive definite. That is, B M is more efficient than B, and it is quite obvious also, because in deriving B, you are not making use of any prior information, but in deriving the mixed regression estimator along with the sample information, we are making use of the prior information. That is, we are making use of the linear stochastic restrictions r beta equal to small r. So, you are utilizing more information, and since you are utilizing more information, definitely it leads to improved estimator also. So, you get improvement over the OLS estimator if you are using the mixed regression estimator. But of course, you cannot derive mixed regression estimator unless you have some kind of stochastic linear restrictions available to you, or you have some kind of prior information available to you, which you can express as stochastic linear restrictions. Then feasible mixed regression estimator. Remember that the expression for this mixed regression estimator involves sigma square u here and here also. So, in practice this sigma square u is unknown. So, the estimator as such is not operational, it is not feasible as long as sigma square u is unknown. So, the only possibility is that we replace sigma square u by its estimator, say s square, and then we get the following feasible mixed regression estimator, say B curl m equal to this. We have simply replaced sigma square u by s square here to get this feasible estimator. Now, suppose you want to test the hypothesis expectation of small r equal to r beta. So, basically what you want to test, say you have this sample information in the form of your model y equal to x beta plus u. So, you want to test whether this prior information is compatible with your sample information or not. Or you can say, if there is close relation between the sample information y equal to x beta plus u and the prior information small r equal to r beta plus v or not. And then for that purpose we use the chi-square test statistic. And the chi-square test statistic is given by say 1 upon sigma square u small r minus capital R B transpose capital R x transpose x inverse capital R transpose plus psi whole inverse small r minus capital R B. Then under the null hypothesis, expectation of small r is equal to capital R beta. And then the statistic follows a chi-square distribution with q degrees of freedoms. Now, to prove the distribution of this statistic, you simply verify that 1 upon sigma u small r minus R B under H naught means under the hypothesis expectation of small r equal to R beta. This follows a normal distribution with mean 0 and variance covariance matrix this R x transpose x inverse R transpose plus psi. And then you can easily verify that this particular statistic follows a chi-square distribution with q degrees of freedoms. And then you can easily form the critical region for testing H naught. But again the problem with this test statistic is that it involves sigma square u, which is usually unknown. So, then we use the statistic f, which has in the numerator r minus capital R B transpose capital R x transpose x inverse R transpose plus psi whole inverse small r minus capital R B divided by the corresponding degree of freedom q upon s square. And then both numerator and denominator follow chi-square distributions, and then we have also divided by the corresponding degrees of freedoms. So, ultimately this statistic follows an f distribution with q and n minus k degrees of freedoms under H naught. And then we reject H naught when f calculated, this calculated value of f is greater than the tabulated value of f, say at alpha level of significance with q and n minus k degrees of freedoms. So, this is the critical region. So, if along with the sample information in the form of your linear model y equal to x beta plus u, you also have some prior information in the form of a set of linear restrictions, but you have some uncertainty about these linear restrictions, or you have some prior information in the form of linear inequality restrictions on the regression parameters or some linear functions of regression parameters. Then you can express such kind of prior information in the form of stochastic linear restrictions. Then if your restrictions are stochastic in nature, you cannot use the restricted regression estimator, because it may lead to biased estimator. So, in that case we have developed the mixed regression estimator, which utilizes both the sample information as well as the linear stochastic restrictions to obtain the estimator. and we have also studied the properties of the mixed regression estimator, and then we have observed that the mixed regression estimator provides an improvement over the ORS estimator, provided you have some prior information in the form of stochastic linear restrictions. So, this is where I am going to stop. Thank you.
Many a times we all think, who am I? Why am I doing whatever I am doing? Why do I feel attracted towards others? Why do I feel very aggressive in certain instances? Why certain people or certain type of acts, they repel me? Why is it that I always search for certain things which look very, very ambiguous? These are the things, these are the questions that all of us experience, all human beings. And you would realize that many a times certain domains of knowledge, especially within social sciences and all sciences at large, when you look at it from a philosophical point of view, they would try to give you the answers to these questions. Now, one of the branches of understanding which helps you understand things much better, which also helps you understand not only what is visibly present before you, what is glaringly apparent to you, rather which also tells you what is not visible at all, what goes within. Okay. And this is the subject knowledge, what is called as psychology. It is not only that it helps you understand the manifested behavior, the overt behavior, how you talk, how you speak, how you say it, how you interact, how you respond, not only that, but also what goes within, what makes you do this, what makes you think this way, what makes you act that way. Why is it that certain things you appreciate, certain things you feel attracted towards, and why is it that many a times in certain type of situations you feel you should completely go out of it, you should not get anyway involved into it, the repulsion. Why is it that certain acts, although you do not appreciate, still you get involved into it? Then you reinterpret your own behavior and you start giving birth to certain type of experiences, shame, guilt, pleasure, appreciation. You see world in a particular way, you analyze it in a particular way, you derive emotion out of it, feeling out of it, and the mix of what you perceived along with what you experience, it makes you act in a particular way, respond in a particular way. Your response is received by somebody else, and then the other person also responds in that situation. Now, there are situations where several people interact simultaneously, the situation remains constant and different people interact at the same time. You realize that your identity gets lost. You are not an individual, you act what is called as group behavior. You realize that you do not have an explanation for either favoring somebody or completely being unfavorable to the other person. You later on realize that it was a favorable or an unfavorable attitude towards that individual. You realize that you repeat certain form of behavior. Why? You do not know. People tell you that such type of repetitions are not normal. human beings largely do not do that. And then you realize that okay, this is a particular pattern of a behavior for which I require the help of a specialist. The specialist tells me that this pattern of behavior is given a particular taxonomy, a particular nomenclature, which is either some aberration in the normal behavior, it is a neurotic form of a behavior, psychotic form of a behavior, it could be a psychosomatic response. And psychology, it covers all of this. So, if you want to understand yourself, if you want to understand others, this is the subject which helps you achieve that target. It is behavioral sciences that makes you understand human beings, human responses, human existence in complete totality.